try to illustrate a lot of it with, or some of it with Matlab examples. First of all, a very theoretical point, something that was discussed and invented by Eugene Wigner, who was a Nobel laureate at Princeton and wrote a famous book on group theory, which actually is a very nice introduction to group theory. So you might consult it at some point. I think it's called Group Theory and the Quantum Mechanics of Atomic Spectra, something like that. Anyway, what he showed was that if you have a symmetry in quantum mechanics, then it either has to be linear and unitary, which is the ordinary kind, or antilinear and anti-unitary. And I'll say in a moment what we mean by symmetry. And antilinear and anti-unitary are very strange, because what happens is you basically complex conjugate and transpose everything, and that's defined by these equations. So let me get back to the more important point of what a symmetry is in quantum mechanics. It's a map of states, so every state goes into an image, and it preserves the probabilities, which are the absolute value squares of the inner products. And as I said, Wigner showed that you either got linear and unitary, or antilinear and anti-unitary. Anyway, we were talking last time about determinants, and we know this is the standard formula for a 2x2 determinant. What I think I didn't mention last time was that you have two vectors, V and W, and you take their determinant, you make a matrix out of them. Then the determinant, or the absolute value of the determinant, is the area of the parallelogram defined by the two vectors. And one way to check the formula is to basically take the vector V and lay it on the x-axis with its origin at with the tail end at the origin, and then look at the vector V and then form the parallelogram, and you can see that its area will be this. Of course, for a 3x3 matrix, you use this anti-symmetric symbol, and you sum this way or you sum that way. And so we knew some of this before. The volume of a parallelepiped defined by three vectors is given by the absolute value of the determinant of the three vector. Laplace showed that in general, in terms of an anti-symmetric symbol here, I've been calling it the Levi-Civita symbol, but since Laplace was using it a long time ago, it probably was invented by somebody else. Anyway, the determinant of an n by n matrix is then this n-dimensional anti-symmetric symbol times a sum over all the row indices, with the column indices arranged this way. And Laplace showed that you could write that in terms of what we call cofactors. And the cofactors are a phase factor times the determinant of the matrix of lower order, n-1 by n-1, of the matrix A without its ith row and kth column. Anyway, I think you know all this, so let me skip through that. and get to the result that I think we discussed earlier, namely the determinant of any matrix whose columns are linearly independent vanishes. And the same thing if the rows are linearly independent. On the other hand, if the n by n matrix has columns that are linearly independent, then you can use them. Well, first of all, we saw that if you added, say, a multiple of one column to another column, you didn't change the determinant. And so that means that we won't change the determinant of a matrix if we say, add a multiple of column 2 to column 1, or a multiple of column 1 plus a different multiple of column 2, 3, plus a different multiple of column 4. We add all of those to column 1, and in that way we've got a, let me see, I may not have opened chat. Let's just see what's going on here with chat. All right, here's chat. Okay, so please chat. Anyway, so if we do that, what we can do is make, we can convert column 1 into a vector that has C1 in the first row and zeros in all the other rows. And we can do the same thing with column 2. We can make it 0, C2, and all zeros. This is because these columns are assumed to be n-dimensional and linearly independent. And in this way, we can, without changing the determinant, we can convert it to a diagonal matrix with numbers C1 through Cn on the main diagonal. And you can do the same thing with rows. And so that's an important thing. But then if we go back to Laplace's expansion of a determinant in terms of the sum over, let us say here, we're summing over the rows, and we're taking a particular column, we're choosing a column K, and we're multiplying these IK, we're going down the kth column and multiplying each row element of that kth column by the ikth cofactor. And so what we learned from that, we know that that's the determinant. What we learned from that is that if instead of doing IK, we do a sum IK, IL, where L is different from K, then what we've got is Laplace's expansion, but for a different matrix. And the different matrix is a matrix that has 2 copies of the kth column. And consequently, it vanishes. So we get 0 in that case. Whoops. That's the thing. This mouse of mine, if I just look at it cross-eyed, it changes the image completely. Anyhow, what we see then is that this sum, this Laplace-like sum, gives us 0 when K is not equal to L, and it gives us 1 times the determinant of A when K and L are the same. And that then is a formula provides a formula for the inverse of a matrix. And what we can see is, well, the result of the formula is simply that the L-ith element of the inverse matrix is the I-elf cofactor divided by the determinant. And to verify that, we just substitute in this expression like that, and we have CIL AIK over the determinant. This is then delta LK. It's 0 when L is not equal to K, and it's this sum is the determinant, which cancels and gives you 1 when L is equal to K. And so this, well, you can do these examples on your own, but let me just mention one other point that's important. If you take a matrix and multiply it by an upper triangular matrix that has 1s on its main diagonal, you don't change the value of the matrix, because what you're doing is you're just adding to each column a multiples of the other columns. And so that doesn't change anything. And if we now apply that idea to this particular structure here, where we've got these are matrices now that are 2n by 2n, because A and B and I are n by n matrices, we then can see that this product gives us that. Okay, now if we take the determinant and use Laplace's expansion along, let's say, the first column, what we can see is that, well, first of all, we can see that the determinant of, well, the determinant of the first one is the determinant of, what am I saying here? Oh, the two equations are equal, and if we, oh, let's see, I have lost track of how the proof goes. Right, this thing doesn't change the value of the determinant. So that means that the product of these two has the same determinant as just this matrix. So we get the determinant of the first one is equal to the determinant of the right-hand side. And now if we do the ordinary expansion of this determinant, what we find is that the determinant of A times the determinant of B is the determinant of AB. And that is an important result. It's something that I'm sure you already knew, namely that the determinant of a product is the product of the determinants. Here's an example of, in fact, the 2x2 example of the proof. And one often uses just straight lines to indicate determinants. And you can generalize the result, just the product rule, to say that the determinant of the product of, in this case, 26 matrices is the product of the determinants of the 26 individual matrices. And it also implies that the determinant of one, which is the determinant of the identity, is the determinant of A inverse, and that's the determinant of A times the determinant of A inverse. So the determinant of A inverse is 1 over the determinant of A. This is worth knowing, and I urge you to study it, but I don't think we need to dwell on it here. It's extremely useful to play with all upper triangular matrices or lower triangular matrices, and the way Matlab and all modern computer programs for doing matrix algebra, they don't do things in the simplest way that we might imagine. Instead, they use various tricks involving things like upper triangular and lower triangular matrices. These examples, I think you can look at yourselves. I think I'm going to pause now, though, and jump maybe to some examples here this is from the examples file, which I've expanded, and I'll put it on the class website tonight. The eigenvector problem, let's just look at it. A times a vector Z is an eigenvalue times vector Z. If it's a 2x2 matrix, Z is a 2 back to lambda is an eigenvalue. And what we have are, we can think of V1 and V2 to be these two-dimensional vectors, and the eigenvector equation then looks like this. And it's just the statement that the two vectors v1 and v2 are linearly dependent. And that means that the determinant of the matrix formed by these two columns has to vanish. This is a quadratic equation for lambda, has two solutions. Once one has the two eigenvalues, one has two equations. In other words, the eigenvalue equations then look like this, and they say that Z2 is proportional to Z1. Whoops, there's a typo there, so that's equation 1.73. I'll fix that. There should be a Z1 here. They're consistent only if this is equal to that, which means that this is true, and that's just the statement of the determinant of A minus lambda I vanishes. Notice, however, that the eigenvectors are only defined up to an overall complex number. And the reason for that is that if we look at this equation, if we have one eigenvector z that satisfies this equation for a particular eigenvalue lambda, we can multiply both sides of the equation by c, where c is any complex number, and we see that the eigenvector cz is an eigenvector of the matrix A with eigenvalue lambda, the same eigenvalue lambda. And that's why in quantum mechanics, eigenvalues are only defined. We always say there's always an arbitrary phase factor, and that's assuming that we've already normalized the states. So I hope you can all send me questions via chat. We haven't had any so far. So let's just see once again a consequence of the fact that the eigenvectors are only determined up to an overall factor. Namely, we can just, if we imagine that the eigenvector z, which is a two-dimensional eigenvector, if we assume just for now that C2 isn't zero, then we can divide the eigenvector by Z2, and then the eigenvalue equations up here just become simpler. It's just W times 1 minus lambda plus A12, and then this equation. And the second equation just tells you immediately that lambda is W A21 plus A22. We can substitute that into the first equation, and then we get a quadratic equation for W, and W is the ratio of the two roots. Of course, there are two solutions, so we get two values of W. Those are the two eigenvectors, and then we get the eigenvalues immediately from the top of this equation, that the eigenvectors are like that. So for 2 by 2, we can do solve the thing with our fingers, but things get a lot more complicated as n rises, especially if we if we just proceed simply. For example, if we say, well, the n by n, if we have an n by n eigenvector equation like this, well, the eigenvalues must satisfy this equation. This is an nth order polynomial equation. It's called the characteristic polynomial. And in fact, if I grab Matlab over here, let me do you a live example here. Let's just set m equal to rand of 5. So this will be a 5 by 5 random real matrix. And if we just say char poly m comma, well, I don't know if I can do lambda. Let me just, I'm not sure how good I can do that. Okay, so that is the the polynomial, God, I think I need to, anyway, the characteristic polynomial then is x to the 5th minus some huge number times x to the 4th divided by another huge number plus a gigantic number, x cubed divided by a gigantic number, minus a humongous number times x squared divided by a humongous number. And then, what is the biggest number I've seen in a long time, times x with a minus sign divided by another huge. And then we have a constant, and in fact, its constant is a fraction of 2 simply absurdly big numbers. All right, so that's the characteristic polynomial of this matrix. One can see that, well, I don't know why these things weren't, there's presumably a Matlab flag that I don't know that would, that would compute these ratios instead of giving us everything in all that complexity. So let's see, we have an anonymous question. How do we come up with those constants? Which constants? Do you mean the characteristic polynomial? And just to tell you what you would do is you would let me not do it in MATLAB because that would involve too many mistakes, I'm afraid. But what you do is you compute the determinant of the matrix. In this case, it would be a matrix M minus lambda I, and M is that 5 by 5 matrix that you saw a moment ago. And then you subtract lambda times, and then you compute that 5 by 5 matrix. And when you do that, you get something that has, when you compute the determinant, if you just, one of the terms is going to be minus lambda to the 5th. And so that's the first term. And what MATLAB did was multiply that by a minus sign to give a positive leading term. Things are much simpler for, in fact, I can maybe give you an example. So let's just say, here, let me do it live for you on the screen. N equals rand of 2. Okay, there's that. Now we'll do char poly n comma y, say. Oops. Poly, well, I don't know why it wanted x, but let's do x then. Okay, so somehow it has a prejudice in favor of x. And so the polynomial is x squared and then minus that. And the equation that one would have would be to solve for those two, set this equation equal to 0. And I think the MATLAB trick is solve, and then I'll grab this, which is huge, equals 0 comma x. And there it's given us the answers, but I would really like to know what those are. Let's try eval with answer, but I'm not sure that will help. Ah, yes, eval then in MATLAB gives you a human readable formula for that. And just to see that this is right, let's use MATLAB to find the eigenvalues just directly. And we just say eigen. And there are the eigenvectors, eigenvalues, and you see they're exactly the ones that we got by setting the character, having Matlab compute the characteristic polynomial and then setting the characteristic, looking for the roots of the characteristic polynomial. And those roots are the places at which the determinant of n minus x times the 2 by 2 identity matrix that vanishes. And so we get these eigenvectors, eigenvalues, sorry. Okay, so someone points out, all right, so let me try the suggestions that have come via chat. All right, so that gives us the answer, but with full, all the digits. Okay, so let's jump out of Matlab for the moment and go back to this. All these results hold, of course, for n by n matrices. And in particular, the n by n determinant A minus lambda I vanishes if and only if lambda is an eigenvalue of the n by n matrix. So that means that this is the eigenvector, eigenvalue equation, and that's equivalent to the determinant of A minus lambda I equals 0. This thing on the right, of course, just gives us the eigenvalues, which are the roots of the nth order polynomial equation that arises when you take the determinant. And that's called a characteristic polynomial. Now, computer programs that do this, in particular Matlab, don't do things in a straightforward way. They use techniques of numerical linear algebra. And the reason for that is that the determinant of an n by n matrix has n factorial terms. And n factorial is something that becomes unmanageable when n is greater than 10 and just positively hopeless when it's greater than 20, because factorial 10 is 3 million, over 3 million, and factorial 20 is over 2 times 10 to the 18th. So these things are absolutely impossible. Right, someone just pointed out in chat that that the class website does not have the latest version of examples. That's right, I didn't upload it. I wrote it this afternoon. I'll upload it tonight. But you'll have it within a few hours. So computer programs that solve for eigenvalues, eigenvectors, and all sorts of other things you can do with linear algebra use efficient algorithms. And one of these, I was surprised to find, was invented quite recently in 1938, actually. Well, that's recently in my book because it's 3 years before I was born. And this is called the Lu Decomposition. And it was invented by a Polish mathematician, Tadeusz Banachewicz. Of course, there's a better way to pronounce that, but I don't know what it is. If his name had been shorter and easier to pronounce, the Lu Decomposition would be probably named after him, but instead, most people have no idea how to pronounce that name, and so they just call it the Lu Decomposition. So let me show you what it is for a 2 by 2 matrix. The idea is to factor the 2 by 2 matrix into a lower diagonal matrix with 1s on the main diagonal and an upper diagonal matrix, period, an upper diagonal matrix. And now, if you multiply these two matrices together, you see what you get is alpha, beta, z alpha, z beta plus gamma. And you can then see by comparing this side with that side that you get that alpha has to equal A, beta has to equal B, and Z alpha has to equal C. So Z is C over alpha, which is C over A. And Z beta plus gamma has to be D. So gamma is D minus Z beta, which is D minus C beta over A, which is D minus BC over A. So the LU decomposition of the matrix A is, it looks like that, where this separates the two columns. And Matlab can do this for you. And what you do first is to tell Matlab that A, B, C, and D are going to be symbolic variables. And then you create a symbolic matrix like that. And there's the matrix. And then you say LU inside brackets equals Lu of A. And indeed, it gives us what we found just using our fingers, namely that the left-hand lower diagonal matrix with ones on its main diagonal is this, and the upper diagonal matrix is that, which is exactly what I wrote up here. And then we can check by taking the product of L times U, and what we get is the original matrix A, B, C, D. So Matlab's web pages describe this and other ways to decompose a matrix and to find its eigenvectors and eigenvalues. There are all sorts of techniques. Cleve Moeller, who used to be the head of the computer science department at UNM, was an expert in numerical mathematics. That is to say that the ways to do calculations numerically, ways that are both efficient and control the errors. One of the things that he focused on a lot was being certain that the errors in any calculation were known, and errors, by errors, I mean round-off errors. That's what he meant by that. Now the LU composition, one of the decomposition, I should say, lets one compute determinants very easily. And the reason is that the determinant of a product is the product of the determinants. On the other hand, L is in general lower diagonal with ones. And so if you just do the Laplace decomposition, all you have are, you just have a bunch of ones. The determinant of L is just one. Let's see, there's a, oh, right, okay, so somebody pointed out why it was that Matlab refused to use Y. It's that I hadn't defined Y as symbolic. If I had, it would have proceeded happily and given us the characteristic polynomial with Y as a main variable. Thank you. So let's see, where were we here? Yeah, so the point is that one of the many advantages of the LU decomposition, which is just famous and basic and used all over numerical linear algebra, is the determinant of a matrix. The best way to do the determinant of matrix, or no, a way that's a lot better than, in fact, it probably is the best way to do, a good way to do the determinant of a matrix A is to do the LU decomposition, to recognize that the determinant of A then is determinant of L times determinant of U. The determinant of L is equal to 1. And then if you compute the determinant of U, you see U, for example, is something like this. So you go down the first column and you have A, and it's A times this. You're done, because the other thing is B times 0. So this is just the product of the diagonal matrix elements. Well, that works in n dimensions. So the determinant of U in n dimensions is just the diagonal elements of U. So there one has, instead of computing n factorial terms, So imagine you have a 20 by 20 matrix and you do the Lu decomposition. Well, now, you don't want to do that by hand, but if you do it either laboriously by hand or you let Matlab do it, you can then compute the determinant by just taking the product of the diagonal elements. That's just multiplying 20 numbers together. And it's, just ever so much simpler. And in the 2 by 2 example, the determinant is that, which is what we had earlier. Let's see how Matlab does eigenvectors and eigenvalues. Let me give you some examples. And I don't know what Matlab does. I think they probably use something more sophisticated than just the Lu decomposition. In fact, one thing that they do, I know, is that they do something called pivoting. That is to say, they put in a third matrix that interchanges the rows or the columns of one of the matrices in order to minimize round-off errors. But that's all behind the scenes when you actually do Matlab. Although you can make it visible, that is, you can have it give you the pivot matrix. Anyway, let's first make a real 3 by 3 matrix. So M is rand of 3. E equals Ig of M gives you the eigenvalues. Notice they're complex, even though M was a real matrix. And the reason they're complex is that M is not Hermitian, and M is not Hermitian because it's not symmetric. If it were symmetric, it would be Hermitian. Now, you might ask, well, does it have to be symmetric to have real eigenvalues? And no, I imagine that it could have eigenvalues that are, it could be real asymmetric, but still have real eigenvalues. But in general, an n by n real matrix has complex eigenvalues and complex eigenvectors. So if we do Vd equals Ig of M, then we get the eigenvectors, and we see they are complex. These are the three these are the three eigenvectors. And the eigenvalues, for some reason, the eigenvalues are displayed as a 3 by 3 matrix. Oh, the reason for that is that you can then take V times D will give you the original matrix M. So let's see that trouble. All right, let's start all over again over here. Let me see if I can do this quickly. So M equals rand of 3, say, and then Vd equals Ig M. Okay, and so now V times D. Whoops. He did not give me, maybe it's D times V. Well, okay, there must be a pivot in there. That's the problem, I think. All right, so skip that. I'll try to resolve that in an example tonight and maybe add it in there. So let's do another example here. Let's generate two 4x4 matrices, multiply one by I, and add them together to get a 4x4 complex matrix C. We can then get its eigenvalues as Eig of C. So R is equal to rand of 4. There we have R. C is equal to C, R is equal to rand of 4, and then I make C as R plus I times rand of 4. So this is then a complex matrix, complex 4x4, E equals Eig of C, and we get 4 complex eigenvalues. Oh my God. Someone just pointed out that I did not start recording. Damn it. Oh, Lord. Okay, well, I'm recording now, but I'm sorry, I forgot to. Oh, somebody else recorded it? Well, that's absolutely wonderful. Thank you. That is brilliant. I'm really sorry, though, about that. So why don't I check by email with Yu Chia-Lin later. She recorded it, and so I think we'll be able to have a full copy on the class webs on YouTube. Boy, that was stupid. Oh well. The reason I didn't, one reason why I forgot is that I started the session 10 minutes early or so, and I didn't want to start recording when I started the session, and then this forgot to start it. Damn it. Okay. So this, if we do the 4x4 case, the complex E equals Eig C, we get the eigenvalues there. If we want the eigenvectors and the eigenvalues, we do VD equals Eig C, and there are the eigenvectors, and the eigenvalues are the diagonal elements of this 4x4 matrix. So those are all the examples that I have done so far today. So let's go back to the class. Well, to the book, basically, and the main class notes, and go to some more theoretical topics, which in any event we have to go through. This is Jacobians, and so the idea is you might be doing a multiple integral over a certain region in the x-plane, x1, x2, and the area element is dx1, dx2. And then you might say, well, you want to change variables to y1 and y2. And the question is how to do that. And I think you know how to do that, but let me show you anyway. If x1 hat and x2 hat are unit vectors in the x1 and x2 directions, then if we change the new coordinates by dy1 and dy2, the changes in the point are partial x1, partial y1 times x1 hat plus partial x2, partial y1, x2 hat times dy1, and the change in the point in the y coordinates, the second y coordinate of the point are I'm sorry, the change in the second y vector is dx1 x1 hat plus respect to y2, x1 hat, and the partial of x2 with respect to y2, x2 hat times dy2. These vectors then, dy1 and dy2, define a parallelogram whose area is the absolute value of the corresponding determinant. And the determinant itself is what's called a Jacobian. And what we do to get the same area element as dx1 dx2 is we use this Jacobian, this absolute value of the Jacobian times dy1 dy2. That gives us dx1 dx2, the same area, and we do the integral like that. In 3 dimensions, you have when you change the new coordinates, yj, the point moves in this way, and it looks like that. And the volume element then is the volume of a parallel pipette, and it's the absolute value of the Jacobian. And so the formulas then are like this. And for n-dimensional integrals, it's that you have dxn equals dyn times this Jacobian, or this absolute value of the Jacobian. And this is then the Jacobian. And since the determinant of the transpose of a matrix is the same as the determinant of the matrix, some people write Jacobians with their rows and columns interchanged. In other words, they would have this row going down, and that row going down over there. Now let's go to systems of linear equations. In particular, let's suppose we have an n by n system of linear equations, or an n by n matrix. A vector x equals y. And what's useful is what we can do, of course, is if this matrix has an inverse, then we just multiply both sides of the equation by the inverse, and we get that x in matrix notation, this is ax equals y. We then just get x equals a inverse y. And of course, Matlab can do that for you. And the way I use Matlab, if I don't know the command, I Google it, and you quickly get the command. What I found, though, is that many of the Matlab web pages are not helpful. But some of them are, and you can generally eventually find what you need. So when A is non-singular, this is the unique solution to these equations. And let's remember, the way to form an inverse, or at least the clumsy way to form an inverse, is using the characteristic polynomials and not the characteristic polynomials, using the cofactors, the matrix of cofactors, transpose of the matrix of cofactors divided by the determinant. And the way you compute the determinant is that you use an Lu decomposition, for example. If the determinant vanishes, then the columns are linearly dependent, and that means then that A times Z is 0 for some non-zero vector Z. So if AX equals Y, then so does X plus CZ. In other words, A on X plus CZ is AX plus CAZ, and that's also true because this vanishes. So if the determinant of A is 0, you may have solutions, but they're not going to be unique. In fact, they will not be unique. There'll be infinitely many other solutions. You may have, if it's a 10 by 10 matrix and it's singular, which is, say, its determinant vanishes, then you might have 5 linearly independent solutions, but the rest of it, but each of those 5 will have infinitely many solutions. In fact, a 5-dimensional space of solutions. Now, what's equally or more interesting is the case when you have an n by n matrix, an m by m matrix, I should say. Well, when you have more equations than you have unknowns, when you have, let's look at it this way. When you have m equations and you have n unknowns, and this is then undetermined. No, I'm sorry, I got it backwards. This is stated correctly, and I was just jumping to this case. So let's go to the more interesting case. Yeah, and that's the case where you have too many equations and not enough variable, not enough unknowns. So you're trying to solve m equations, and you only have n variables. So this is called overdetermined, and in general, it has no solution. But it does have an approximate solution, which was invented by Gauss, and the trick here is to compute the error. Well, the error is the sum over the large number of required solutions, and this linear combination's best guess at each solution. And so you have yi minus the sum on k of aik xk, and you take that thing squared, and then you sum over I. And that gives you then the total squared error. And you then the natural thing to do is to minimize the error. And the way you minimize this is a function now of these n unknowns. And the way you minimize the function of the n unknowns, the n unknown x's, k goes from 1 to n, is that you set the partial derivatives of the error, or the squared error, equal to 0. And the partial derivative then is this. And in matrix notation, after you've straightened out the minus signs and so forth, what you have there is that A transpose Y is A transpose AX. And if A is real, then A transpose A is non-negative. And so it probably has an inverse. It might have a 0 eigenvalue, but so it's non-negative. So all its eigenvalues are either 0 or positive numbers. If they're all positive numbers, then it has an inverse. And then what we do is we take the inverse of this positive matrix and say that X is equal to A transpose A inverse times A transpose Y. So that's basically how that was Gauss's solution. If A and Y are complex, then what one finds is that one gets a matrix A dagger, and one sets A equal to A dagger A inverse times A dagger Y, assuming that this actually has an inverse. These matrices, these quantities here, A transpose A inverse times A transpose, this is called a pseudo inverse of the matrix A. And this thing is also a pseudo inverse. And there's a section about pseudo inverses, section 33. They're called the Moore-Penrose. These links, well, all right, anyway. Let's go now to Lagrange multipliers, which is an important technique, and it's something that you probably have seen in an earlier course, but it's nice to review it, I think. So the maxima and minima of a function of n variables are just the points at which all the partial derivatives vanish, and these are called the stationary points of the function. For example, if you have this quadratic polynomial, then the roots are simply, in this case, they're all equal to 0. Lagrange showed how to find the extrema of a function if you want to find the extrema subject to some constraint. So in other words, suppose you have one constraint such that C of x is 0. And then what we're saying is that the gradient should vanish in directions that preserve the constraint. And so what we want is we want dx dot grad f to vanish for all dx such that dx dot grad c vanishes. In other words, for all dx's that maintain the constraint. So we don't care if about points. Okay, there's a question here. What does it mean to say among the points where the gradient vanishes? Are there points where the gradient vanishes? Well, okay, the question is about what's the issue that we're trying to do. We're not trying, in this case, to find the minima and maxima of the function. We're trying to find only the minima of and maxima of the function subject to the constraint. So in other words, suppose you're walking on a path up a mountain, and some of these mountains, particularly the west side of the Sandias, you have trails that go up the mountain, and those trails, you're expected to stay on the trail. And in fact, in many cases, you better stay on the trail, because if you go off to the right by more than about a few feet, you find that you fall down the mountain. And on the other hand, if you go to the left by more than a few feet, well, you're winding up having to climb very steeply. And so if you wanted to find the maximum or minimum, local maxima or minima of your height or your altitude on the trail, then you only keep track of bumps on the trail. You don't worry about the fact that that there's an even bigger maximum if you go to the left, because there you'll be climbing steeply up the mountain. And you don't worry about the fact that to the right, if you jump off to the right, you'll quickly find a local minimum that might be 1,000 feet below you. So that's what's meant here. And so in other words, we're only interested in points that satisfy this equation if, in other words, dx dot grad f equals 0, if dx dot grad c also vanishes. And so the way we satisfy both the constraint and the fact that the gradients are parallel is that we define a different function. And this is a kind of Lagrange, we call it Lagrangian. It's the original function minus an arbitrary parameter times the constraint. And so now this is if this x has n is a function of, if x has n components, then this is L is a function of n plus 1 variables. And we look now for the extrema of this, and we forget about any constraint because we've already included it. And so the constraints then are the partial of L with respect to all its n plus 1 variables, the n x's, and lambda. And that gives you these two equations, which then give you, which you can then solve both for the local, for the extrema on the path, or the extrema subject to the constraint, and you also wind up with a value of lambda if you want it, but it's rarely useful. If you have k constraints, you do the same thing, but now you're even more more fussy about which points with vanishing gradients you would accept. And in this case, you only accept points such that dx dot grad f is 0 for dx's that make that satisfy, that are in the direction of no change in any of the constraints. And so in other words, you want the gradient to be a linear combination of all of the constraints. And because then dx dot grad f will vanish if dx dot grad cj vanishes for all the j's from 1 to k. And the extrema must satisfy these constraints. And so we have n plus k equations. And the way we solve them all is we set L of n x's and k lambdas equal to this, where the n x's are in here. And then we ask for the absolute extrema of this quantity, this Lagrangian, and that means we set its partial derivative with respect to each of the n x's equal to 0, and a partial derivative, its partial derivative to each with respect to each of the k lambdas equal to 0. One example that might be worth doing here is to say, suppose we want to find the extrema of a real symmetric quadratic form. So that's something a sum over I and j, xi, aij, xj, and we can write it as x transpose a matrix x. And the constraint is that C should vanish, where C is x dot x minus 1. And so what we do, and of course I could have written this as x transpose x. And so the matrix A, we're assuming is real and symmetric. And so we set the Lagrangian equal to this. This is the thing we want to minimize or extremize, and we put in the constraint. And then we set the partial derivatives equal to 0. And the other equation, the partial of L with respect to lambda, just enforces the constraint. So what we have then is that AX is lambda x, and x dot x equals 1. The AX equals lambda x comes from this equation. If you put this term to the right-hand side, cancel the 2's, you just have in matrix form AX equals lambda x. So what we found out is that X is an eigenvector of the matrix, the real symmetric matrix A, with an eigenvalue lambda. X has to be normalized. And so it's the eigenvectors of A that are extrema of this quadratic form, subject to the constraint that they be normalized. So more about eigenvectors and eigenvalues. If a linear operator A maps a non-zero vector into a multiple of itself, then it's called an eigenvector. And lambda is the eigenvalue, of course. We can write this in Dirac notation in this way. And as I said many times, Dirac notation is extremely useful. The matrix elements of A appear this way, or equivalently, the inner products of the linear operator A with the bra K and the ket L are the matrix elements of the matrix A. These inner products are the elements of the vector U. And a subspace spanned by any set of eigenvectors is left invariant by the action of A. So A on any linear combination of the eigenvectors is, of course, a different linear combination in general of the eigenvectors, but it's still a linear combination of the eigenvectors. So that means that eigenvectors span spaces that are invariant under the action of A, or under multiplication by A. Something a little bit surprising when you first see it, perhaps, is that the eigenvalues of an orthogonal matrix are actually phase factors. This gets back to what we said earlier, namely that you can have a real matrix, and if it's not symmetric, and this one, of course, is not symmetric, then it's not Hermitian, and well, it may not be Hermitian. This one is not symmetric and not Hermitian, so its eigenvalues are complex, and the eigenvectors in this case are also complex. I think we can probably skip that, but I think you should read it. The eigenvectors of a square matrix, well, we've gone through this in many examples, so we know that what you do is you take the Lth eigenvector A on the Lth eigenvector is the Lth eigenvalue times the Lth eigenvectors. That's this matrix equation. This is that matrix equation, and what this is saying is that the elements of the vector times the column vectors vanishes, which is saying the columns are linearly dependent. The determinant then vanishes if lambda is an eigenvalue. And the vanishing of that determinant, well, that is, if this is an n by n determinant, then this is something with, in general, n factorial terms, but if you use an Lu decomposition, it's not so bad at all. And that determinant is then a polynomial in lambda of order n, and the leading term is -1 to the n, lambda to the n. The first term is what you get when lambda is 0, and that's just the determinant of A. By the way, this is the determinant of A. It's not the absolute value of anything. And then you have all these other terms, and one of them is the trace of A. Let's see, there's a question here, geometrically. Right, that's right. You want the gradient of F and the gradient of the constraint to be parallel if you're in one variable, and if you're in more than one variable, then you want the gradient of F to be equal to a linear combination of the gradients of the constraints. Notice that remember we found that the trace was invariant under a transformation. If you put a matrix here and another matrix there, for example, you put an S here and an S inverse there, since the trace is cyclic, you can move the S to the right, then you have S inverse S, and that goes away. So the trace is invariant under what's called a similarity transformation. Also, the determinant's invariant under a similarity transformation because the determinant of a product is the product of the determinant. So you have the determinative S, determinative A, determinative S inverse. The determinative S inverse is the inverse of the determinative S, so that cancels. All of these terms, all the other coefficients of lambda are also invariant quantities, invariant invariant functions of the matrix A. They're all base, and the P's are basis independent. The P's, that's what I just said, they're basis independent. Well, actually the whole proof is here, and instead I just did it in my head. So if you replace A by A prime equal to S inverse AS, then the characteristic polynomial of lambda A prime looks like this. You replace that this way, you then you can put the S's on either side of the identity. You then factor the product. Well, it is factored. You then have the product of the determinants. This one cancels that one. You're back to this. So it's invariant. Now we're going to, when we do complex variable theory, we'll learn that any n-dimensional, any order n polynomial equation has n roots in the complex plane. And so that means that any n by n matrix has n eigenvalues and n eigenvectors. Now, these n eigenvalues need not be different, and the n eigenvectors, in general, they are different, but for defective matrices, they can be, they may not be. So basically every n by n non-defective matrix has n eigenvalues and n linearly independent eigenvectors. We just have a few minutes left. Somebody might have an urgent question. So why don't you ask an anonymous urgent question if you can find the words to formulate it in just a few minutes. Anyway, I'll leave that to you and I'll just go on for a moment here then. The n by n diagonal matrix is what's called, and it's diagonal with the lambdas, the eigenvalues on the main diagonal. This is called the canonical form of the matrix. And so the matrix V, whose columns are the eigenvectors, is called the modal. It's called the modal matrix, and AV is VAD. Oh, that's why I screwed up last time with Matlab. I wanted to say that A was VAD. It's AV is VAD. So that's what I should have done. In fact, maybe I can illustrate that if I can grab Matlab really quickly over here. Whoops, where did it go? Okay, there it is, and it's much too big here. Okay, so here we had M is the matrix. So it is, so this equation, where the hell was the equation? Yeah, A, so A is M. So we have the equation M times V, and we get that. And now we do V times D. I hope I've done that right. We get the same thing. So here I've illustrated in Matlab this equation, namely that the matrix times multiplied by the matrix of eigenvectors, which is called the modal matrix, is the modal matrix times the diagonal matrix of eigenvalues. And of course, that's the reason why Matlab expresses the eigenvalues as a matrix, as a diagonal matrix, because you then have it handy so that you can do things like I just did here. Okay, well, we're basically out of time. Let me once again apologize for having failed to record. So let me go over here and stop my recording. So I'm going to do that. And remember, we'll have class tomorrow at 5:30. It's a Wednesday class, which is going to go on a UNM website, so you can appear in full form. You don't need to be anonymous, invisible, silent, or anything like that. You can shout and scream and play horns. Whatever you want to do is fine. Okay, so goodbye, everybody, but maybe I should keep talking to Yu Lin. So let's see if Yu Lin can become yeah, if anybody wants to talk, I'm not recording. And Yu Lin should also stop recording if we're going to be talking. How can I make this bigger?